Hello, and welcome back to From Zero to Zeta. I'm your host, Rowan McKee. Before we dive in, few quick reminders. First, join our community Discord for questions, discussions, and live events. I also run gaming channels on YouTube and Twitch under the name Zero to Zeta Gaming, with a special focus on chess and strategy games. Links for both the Discord and the gaming channels are in the description. And thank you to everyone who's already subscribed. If you haven't yet, please like and subscribe. It really helps grow the channel and makes it possible to create more of these episodes. Today, we're going to slow down and connect some of the language we built last time to a powerful organizing principle, equivalence classes. From there, we'll build up, carefully and visually, to quotient groups, cosets, and the realization that modular arithmetic is not just a trick with remainders, but an instance of a deep structural pattern. Roadmap for the episode, we're going to define equivalence classes with concrete visual examples. We're going to use a subgroup H to induce an equivalence relation on a group G. See how the resulting classes are exactly the cosets of H, and assemble those into the set G quotient H. We're going to ask the key question, when is the operation on cosets well defined? We'll test it on examples and hint at the special subgroups where it always works. We're going to revisit modular arithmetic through this lens, the quotient NZ as a quotient group, and compare Cayley tables to see the isomorphism with Cn. The headline intuition is this. Equivalence classes let us treat many elements as the same for the purposes we care about. Cosets are those classes when the purpose is group structure. By the end of the episode, Z quotient NZ and Zn will feel like two names for the very same object, and you'll see exactly why. In our previous episode, Building the Language of Groups, we made group theory precise by introducing standard notation and symbols. We saw how mathematicians shorthand big ideas into compact, reusable expressions, and we practiced with visual tools that help us see structure at a glance. To recap, we covered the four axioms of a group: closure, associativity, identity, and inverses. We gave concrete examples: integers under addition, geometric symmetries, and permutation. We saw modular arithmetic as a standard finite model for group structure: cyclic versus non-cyclic groups, abelian versus non-abelian groups, and subgroups living inside larger groups, and how they inherit the group operation, equivalence relations, reflexive, symmetric, and transitive properties. But notice, while we introduced the idea of an equivalence relation, we never defined what an equivalence class is. That's the missing piece we need to connect subgroups to cosets, and cosets to the structure of modular arithmetic. That's where we'll begin today. Let's begin by filling in the missing step. What exactly is an equivalence class? Definition. If congruence is an equivalence relation on a set S, then for any element A in S, the equivalence class of A is the set X in S such that X is equal to A. In other words, A is the collection of all elements in S that are considered the same as A under the relation congruence. Equivalence classes partition the set S. Every element of S belongs to exactly one equivalence class, and no two classes overlap. So some examples: integers mod 3. Define A is congruent to B mod 3 if A minus B is divisible by 3. Then the equivalence classes are the multiples of 3, the multiples of 3 plus 1, and the multiples of 3 plus 2. Think about time on a clock. After 12 hours, the system resets and we're back to where we started. Saying 2 times our equivalent mod 12 is just recognizing that the structure the clock already enforces. For example, 3 o'clock and 15 o'clock look different as numbers, but on the clock they fall into the same class. We say 2 triangles are equivalent if one can be rotated to perfectly overlap the other. Then all rotated copies of the same triangle fall into a single equivalence class. This is how we get triangle congruence. Imagine a game piece on a circular board. Rotating it doesn't change what the piece is or how the game works. It's still in the same state for the rules of the system. All those rotated positions form one equivalence class. An equivalence class is a way of saying different inputs can behave the same way because the structure of the system makes them interchangeable. With integers mod n, the clock structure forces numbers to wrap around. With rotations, geometry forces certain positions to be indistinguishable. Equivalence classes are the mathematical tool for capturing this kind of structural sameness. And this idea of grouping is exactly what will carry us into cosets. Let's start with something very familiar, the integer z, under addition. Inside this group is a subgroup of even integers, 2z. Now, here's a natural question. Given any integer, can we assign it to the nearest even integer that is greater than or equal to it? In other words, can we project the integers onto the even integer? If we define f of n as the smallest even integer greater than n, then we have f of 7 equals 8, f of 12 equals 12, f of negative 3 equals negative 2. This function divides the integers neatly into two categories, those that land directly on even numbers and those that sit one step higher. Every integer belongs to exactly one of these two parallel worlds. This is our first glimpse of something called an equivalence class, sets of numbers that behave the same way with respect to our subgroup. For your convenience, here is the formal definition once again. The equivalence class of an element A is defined as x and x such that A is congruent to x. In other words, the set of all things that are equivalent to each other. In this case, the two classes are the even numbers and the odd numbers. Instead of looking only at even numbers, let's consider all multiples of n. The subgroup is nz. Two integers are equivalent modulo n if they differ by a multiple of n. So a is congruent to b mod n. That means a minus b is in nz. This partitions the integers into n classes, 0 through n minus 1. Let's see a few explicit examples. For n equals 3, we have the multiples of 3, the multiples of 3 plus 1, and the multiples of 3 plus 2. For n equals 4, we have the multiples of 4, the multiples of 4 plus 1, the multiples of 4 plus 2, and the multiples of 4 plus 3. For n equals 5, we have the multiples of 5, the multiples of 5 plus 1, the multiples of 5 plus 2, the multiples of 5 plus 3, and the multiples of 5 plus 4. So far, we've written things like a minus b is in nz, but subtraction is just the inverse of addition. In group language, instead of writing a minus b, we write a to the negative 1b. It should also be noted that this particular notion actually corresponds to the expression negative a plus b instead of a minus b when working with nz. But one is just a negative of the other, so either expression will work. If one is in nz, so will be the other, meaning a to the minus 1 times b is still valid. That means the rule a is congruent to b mod n if and only if a minus b in nz is the same as a is congruent to b mod h if and only if a inverse b is in h, where h is the subgroup nz. This general phrasing works not only for integers but for any group. It is the bridge from arithmetic to abstract algebra. The collection of all these equivalence classes is called a quotient set. Written G divides H. It's the set of equivalence classes where A is in G. In our examples, G equals Z and H equals NZ, so G divides H consists of the n parallel classes we just described. They run alongside each other like lanes on a track, disjoint, complete, and covering the entire group. Next, we'll dissect this new kind of set to see what kinds of structure we can find from it. Up to this point, we've been talking about quotient sets in general, breaking a group into parallel equivalence classes determined by a subgroup. Now it's time to give these classes their proper name. They're called cosets. Definition: let G be a group and H a subgroup. If G is in G, then G8 is the set of all elements GH such that H is in A and G is in G. And this is called a left coset of H in G. The right coset is just the reverse. Here, the element G is called the representative of the coset. Each coset is nothing more than the subgroup H shifted or translated by G. Cosets have some fundamental properties. Cosets of H divide G into parallel non-overlapping slices. Every element of G lies in exactly one coset. And all cosets contain the same number of elements as H. Shifting the subgroup doesn't stretch it, shrink it, or overlap it. It just slides it somewhere else. Think of it like taking a stamp and pressing it repeatedly along a strip of paper. The image is always the same size, but each imprint lands in a different position. That's what cosets do. They tile the group with copies of H. Revisiting earlier equivalence classes, in the section about quotient groups, we saw the integers split into two equivalence classes under the subgroup 2z, the evens and the odds. Now we can name them as cosets, 0 plus 2z and 1 plus 2z. So the two parallel worlds of integers are really just the two cosets of 2z. For integers modulo 3, we saw three equivalence classes when we looked at the subgroup 3z. Now we recognize them as cosets: 0 plus 3z, 1 plus 3z, and 2 plus 3z. The same goes for modulo 4 and 5. For modulo 4, we have 0 plus 4z, 1 plus 4z, 2 plus 4z, 3 plus 4z. For modulo 5, it's 0 plus 5z, 1 plus 5z, 2 plus 5z, 3 plus 5z, 4 plus 5z. What we called equivalence classes before are precisely the cosets of H. Let's look at a finite group, Z6. It's the integers from 0 to 5, with the subgroup H equals 0, 3. This is a subgroup because 0 plus 3 equals 3, and 3 plus 3 equals 0. So the cosets are 0 plus H, which is 0, 3, 1 plus H, which is 1, 4, and 2 plus H, which is 2, 5. That's 3 cosets, each of size 2, perfectly tiling the circle of 6 numbers. And here's a striking observation. In every example we've seen, the cosets are equal in size to the subgroup, and together they partition the whole group. In Z, the subgroup 2Z splits the integers into 2 infinite lanes. In Z6, the subgroup 0, 3 splits the group into 3 cosets of size 2. In Z12, the subgroup 0, 4, 8 splits into 4 cosets of size 3. This is not an accident, it's a deep pattern. Whenever you take a subgroup H of a finite group G, the cosets of H always partition G into equal sized pieces. That means the size of H must divide the size of G. This fact is so important it gets its own name, Lagrange's theorem. We won't prove it just yet, but you can already see it alive in the examples we've done so far. So cosets aren't just abstract classes. They're the familiar equivalence classes we've already been working with, but now understood as subgroup shifts. Next, we'll ask what happens if we try to combine these cosets the way we combine individual elements. That's where modular arithmetic emerges naturally from the coset structure. So far, cosets have just been slices of the group, partitions that break G into parallel classes. But a group isn't just a set. It comes with an operation. That raises the natural question: can we define an operation on cosets? Here's our candidate definition. If AH and BH are two left cosets of subgroup H, we'd like to define their product as AH times BH equals AB times H. In other words, multiply the representatives A and B, and then take the coset of the result. Let's test this on the integers, where everything feels comfortable. Take G equals Z, H equals 2Z, cosets are evens, 0 plus 2Z, and odds, 1 plus 2Z. Now add them. Even plus even equals even plus odd equals odd plus even equals odd, and odd plus odd equals even. It works exactly as expected. In fact, the cosets behave just like the group Z2, so in this case the rule is fine. Here's where we have to be careful though. Think about fractions for a moment. We say that 1/2 and 2/4 are the same fraction. That's an equivalent. But once we make that identification, we need them to behave the same way when we combine them. For example, 1/2 plus 1/3 equals 5/6. We need 2/4 plus 1/3 equals 5/6. That's why 1/2 plus 1/3 doesn't equal 1/5, and 2/4 plus 1/3 doesn't equal 3/7. The results match. If instead 1/2 plus 1/3 gave a different answer than 2/4 plus 1/3, then the identification 1/2 equals 2/4 wouldn't be well defined. That's exactly what's at stake with cosets. If we say two elements represent the same coset, then no matter which representative we pick, the results of operations must come out the same. Otherwise, the definition of multiplying cosets doesn't make sense. So now let's see what happens in a group that isn't as tame as the integers, the Rubik's Cube group. Before we dive in, let's pause. What exactly is a set? A set is just a collection of objects that we've grouped together with no assumptions about how those objects behave or what those objects necessarily are. Just a bag of things we're looking at all at once. Sometimes those things are numbers, sometimes they're shapes or functions, and sometimes, like now, they're going to be operations. So here's the question I want you to consider. What if we take the operations of the Rubik's Cube themselves and treat those operations as the elements of a set? That set will be the one we build a group out of. It's a step of abstraction higher than just looking at cube positions. At first, it might seem more natural to let G be the set of all possible positions of the Rubik's Cube, the solved cube in every scrambled state. But there's a problem. Cube positions don't naturally combine. If I hand you two scrambled cubes, there's no operation that takes one position and multiplies it with another to get a third. What does combine are the moves themselves. If you turn the right face and then the up face, that's a sequence of moves we can write as RU. And importantly, move composition is associative, it has an identity, and every move has an inverse. So when mathematicians talk about the Rubik's Cube group, the group elements are not cube positions. They are all the legal move sequences, and the group operation is composition of moves. The cube positions are the results of applying those moves to the solved cube, but the group itself lives one layer higher. It's the algebra of the move. So here's our setup. G is the set of all legal Rubik's Cube moves with composition as the operation, and H is a subgroup generated by turning the right face R. So we have H equals the identity, one right turn, two right turns, three right turns, and then it comes back to the identity. These are all the pure right face turns. Now let's try our coset operation. Take the coset of right turn moves, RH, and the coset of upturn moves, UH. Our candidate rule would say RH times UH equals RUH. But here's the problem. If we pick different representatives from those same cosets, say R squared instead of R, and U squared instead of U, then the product becomes R squared U squared times H, which is not the same as RUH. Why? Because on the Rubik's Cube, the order of moves matters. RU and UR lead to different outcomes. So RU times RU is different from R squared times U squared. And that non-commutativity makes the coset multiplication misbehave. Different representatives can give different results, and that means the operation on cosets is not well defined in this case. So here's the story. In the integers, everything works beautifully. Operations on cosets are well defined, and modular arithmetic emerges. In groups like the Rubik's Cube, operations on cosets can break down because different representatives don't play nicely with each other. Later, we'll see that the subgroups where this problem never happens are called normal subgroups. But for now, let's stick with the integers where the structure is perfectly well behaved, and see how modular arithmetic falls right out of coset operations. In the last section, we saw a contrast. With the integers, operations on cosets were perfectly well defined. With the Rubik's Cube, they broke down. Why the difference? Because in the integers, addition is commutative, and the subgroup NZ sits nicely inside the group. No matter which representative of a coset you pick, you always land in the same class when you add. For example, working modulo 6, 1 plus 6z is the same as 7 plus 6z. So whether we use 1 or 7 to represent the cosets, the result is the same. That stability is what makes modular arithmetic possible. On the Rubik's Cube, however, different representatives can lead to different outcomes because the order of moves matters. That's what caused coset multiplication to misbehave. So the integers give us the cleanest playground to see how cosets combine into a new group. Let's take G equals Z and H equals 5Z. The quotient set is Z quotient 5Z, which is the set 0 plus 5Z, 1 plus 5Z, 2 plus 5Z, 3 plus 5Z, and 4 plus 5Z. Now let's define addition on those cosets. A plus 5Z plus B plus 5Z is going to be A plus B plus 5Z. Because the choice of representative doesn't matter, this operation is well defined. And with that, the quotient set becomes a group. We can capture the whole structure in this Cayley table. Now let's look at Z5 with addition modulo 5. This is the Cayley table for Z5. Now if we show them side by side, look at the numbers on the left and compare them with the table on the right. They are identical in structure. This shows that Z quotient 5Z is isomorphic to Z5. In fact, for any n, the quotient Z quotient NZ is isomorphic to the modular arithmetic group Zn. That's why we often write them interchangeably. But now you've seen exactly why the notations mean the same thing. So by looking at cosets of NZ and Z, we've rebuilt modular arithmetic from scratch. This is the canonical example of a quotient group, and it shows why cosets are more than partitions. They can carry full group structure. Let's take a step back and see where we've traveled in this episode. We started with equivalence classes, a way of grouping elements that behave the same. We saw how subgroups carve out those classes, leading us to the idea of quotient sets. We gave those classes their proper name, cosets, and explored how they partition a group into equal slices. We defined an operation on cosets and discovered that sometimes it works cleanly, like with the integers. Sometimes it fails, like with the Rubik's Cube. Finally, we saw that when it does work, we can recover modular arithmetic from scratch. Z quotient NZ is isomorphic to Zn. This is the power of quotient groups. They don't just slice a group into parts, they give us brand new groups with their own structure. But the story isn't finished yet. We've seen that coset operations are well defined for subgroups like NZ, but not for subgroups like the right space terms on a Rubik's Cube. So the natural next question is, what special property makes a subgroup behave well enough for coset operations to always work? That property has a name, normality. In the next episode, we'll define normal subgroups and see why they are the key to making quotient groups well behaved in general. Before we wrap up, a few quick reminders. If you enjoyed this episode, please like and subscribe. It really helps us grow the channel and keeps these videos coming. Join our community on Discord. It's the best place for discussion, questions, and live events. And don't forget, I also run gaming channels on YouTube and Twitch under the name Zero to Zeta Gaming, with a special focus on chess and strategy games. That's your thing, come hang out there too. Thanks for watching, and I'll see you next time. And next, we'll dive into the exercises for you to try out these structures and patterns on your own. You may want to pause after each question to try and work out the answers on your own. Now let's get started. First exercise, for each subgroup H in Z12, list all left cosets A plus H and state how many different ones there are. A, H equals 0, 6. The cosets are 0, 6, 1, 7, 2, 8, 3, 9, 4, 10, 5, 11. That's 6 cosets, each of size 2. We've basically split the 12 numbers into pairs that are 6 apart. You could color the 12-hour clock face in 2 alternating colors, and you'd see exactly this structure. B, H equals 0, 4, 8. The cosets are 0, 4, 8, 1, 5, 9, 2, 6, 10, and 3, 7, 11. That's 4 cosets, each of size 3. Now it feels like we've divided the clock into quarters. Every 3 steps you land in the same coset. Nice symmetry. C, H equals 0, 3, 6, 9. The cosets are 0, 3, 6, 9, 1, 4, 7, 10, and 2, 5, 8, 11. That's 3 cosets, each of size 4. This time we're carving the clock into thirds. Notice how the every third number pattern repeats. Another clean division. D, H equals 0, 2, 4, 6, 8, 10. The cosets are 0, 2, 4, 6, 8, 10, and 1, 3, 5, 7, 9, 11. Just 2 cosets, each of size 6. And now we're back to evens versus odds. Half the clock shaded one color, half shaded another. You can really see Lagrange's theorem in action. The subgroup size always divides 12 exactly. Now we're going to explore what happens in the non-abelian group S4 with the subgroup E 1, 2, 1, 4, 2, 4, 1, 2, 4, and 1, 4, 2. A, write out all of the left cosets of H in S4. There are 4 cosets total, these 4. If that looks like a lot, don't panic. The key takeaway is just that the cosets partition S4 into 4 neat slices of equal size. The details are there if you want to check the multiplication. B, compute 1, 3 times 2, 3, and 1, 2, 3 times 2, 3. 1, 3 times 2, 3 equals 1, 3, 2, and 1, 2, 3 times 2, 3 equals 1, 2. This is the part where non-commutativity sneaks in. Even tiny tweaks in the order of permutation multiplication can totally change the result. C, which cosets do 1, 3, 2, 3, H and 1, 2, 3, 2, 3, H represents, and what does that tell you? 1, 3, 2, 3, H equals 1, 3, 2, H equals 2, 3, H, while 1, 2, 3, 2, 3, H equals 1, 2, H, which equals H. So even though 1, 3, and 1, 2, 3 are in the same starting coset, multiplying them with the same 2, 3 coset gave us 2 different outcomes. That's the classic sign that the multiply representatives rule isn't well defined here. The subgroup H just doesn't behave. It's not normal. And that's why modular arithmetic feels so smooth by comparison. If you made it this far, thank you for sticking with me. We covered a lot today, and the exercises at the end are where you'll really get a feel for how cosets and quotient groups work. If you enjoyed this episode, please like and subscribe. It really helps the channel grow. And don't forget, if you're working through the exercises and get stuck, or if you just want to compare notes with others, best place to ask for help or clarification is our community Discord server. The link is in the description. I'll see you there, and I'll see you next time as we dive into normal subgroups.